The next point, of course, is try to solve it. What is the solution of that kind of equation? And I love that line from the video that it says that you can solve it using the time honor technique of guessing, right? The first person who ran into that equation had to guess the solution. So the book says, and here the video uses this function. It says, how about we try x equal a sine of omega t, right? It's just a guess. You plug it into the equation and you see if it satisfies it or not. We're going to do that a little later. But I want to point out that a source of confusion. The book uses this. This is what the video says. This is what the book uses. Which one is right? They're both right. A sine function is a cosine function just displaced, right? In general, actually, the equation that you want to use, which covers that case, and any possible solution of that equation, will have this form. How does this equation cover this case or that case? What would I have to change to get to make this equation look like this or look like this? Well, for this one's pretty easy, right? If phi 0 was equal to 0, then I'm talking about x being a cosine of omega t, correct? But if I chose phi 0 to be minus pi over 2, then you're back to this. Because the cosine of an angle minus pi over 2 is the sine of the angle, right? Cosine of theta minus pi over 2 is equal to sine of theta, whatever theta is. So you will get this equation. Sine. So both equations are right, and the more general solution of the simple harmonic oscillator equation is this one. So you have 1, 2, 3 parameters in this equation that describe the different possibilities, different kinds of motion that you can have that are correspond to a simple harmonic oscillator. The question, let's start with phi 0. So what does determine phi 0? Can I just set it to 0 or minus pi over 2 if I want to? How would I figure out what, if there is any way of doing that, how do I figure out what phi 0 should be? That's going to have to do with the initial conditions. That's right. The initial condition is what's going to determine what phi 0 you're going to use. The initial condition means, translated means, what is the oscillator doing at t equals 0? Right? At t equals 0, when you started your imaginary stopwatch in this, that is describing the motion of this object, when you start t equals 0, where is the object at that moment? Right? Do you always make sure that the object was at an amplitude A, and from that point it's going to oscillate? Or maybe you start the time when the object is at the equilibrium point? It depends how you want to start your watch, at what point you want to start your watch. Or another way to say it, what is the oscillator doing at t equals 0? Where is it, and in which direction it's going? So to see that more clearly, we have to talk about the connection between circular motion and oscillatory motion, which the video makes. And it's a very, very important thing to remember, to understand and then to remember, because for waves, when we talk about interference of waves, the idea of the phase of the wave always gives people a lot of trouble with that topic. And the phase, the idea of phase, is coming from the oscillatory motion. So let's talk about that. So there is a circular motion that can match, that will match the motion of any simple harmonic oscillator that you might have. Okay, you just have to choose the frequency at which the object is moving in a way that it matches the omega that you put in your equation for the harmonic oscillator. So let's focus on the circular motion part, the rotational motion, and talk about the phase or the angle of that object. And then we'll talk about the phase of the oscillator, which, as you can see, the point is that whatever the location of the circular motion, the object that is going in circular motion, is the projection of that motion, right, along the x-axis matches the location of the oscillator, right? We set up things in such a way that that is the case. No matter where the object is, the one that is doing circular motion, if you draw a line all the way down to that crosses the x-axis, that would be coincide with the location of the block, right? At all times it would coincide. So if we talk about, or if we describe the motion of that object moving in a circle, we will know how this guy is moving, right? So let's focus on that then, because that it's pretty simple, right? It's just an object moving in circular motion with constant angular velocity. How do we describe the motion of this object that is spinning around with angular velocity omega? How does the angle, suppose that the object at some time t is over here. So there is an angle here. I'm going to call that angle phi, which is a function of time. Correct? The vector position the object, the vector position is spinning around and it makes an angle phi at some instant of time t. How does phi depend on time? What is the exact function that describes phi as a function of time? Omega is constant. So that means that phi is what? Phi is equal to omega t. Is that it? Why do I need to add an initial phase there, an initial angle there? Well, at t equals 0, I don't know if I'm always going to be able to start with the object right here, right? Which would be the case when t equals 0. Is phi equals 0 always? Well, not always, not necessarily, right? So in general, you're going to have a different phi 0 depending on at what time at t equals 0, where was the object? Exactly where in the circle was the object when you started your time, right? So if the object, if at t equals 0, the object started here when you was moving there, remember that this is moving with an angular velocity omega at all times, the same angular velocity. When the object was here, it had some linear velocity this way, and it's at this location. So if this is what you have, if this is the initial condition that you have, that phi at t equals 0 was equal to pi over 2, then what's my phi 0? Pi over 2. Skip this, the initial here. Let's do another one here. If at t equals 0, as we just said, if at t equals 0, phi of 0 was equal to 0, then phi sub 0 is equal to 0, right? So this is one case. This is another case. These are all different initial conditions, right? Once you decide what's your initial condition, you have to stick to that initial condition, and that describes your motion. Okay? But you could have this initial condition, you could have this one, anything in between those two, right? What if at t equals 0, your particle moving in circular motion was actually here? If at t equals 0, the particle was here, then that means that phi, as a function of time, but at time t equals 0, is equal to pi Remember the particles moving around like this. And that implies that phi 0 is going to be pi. Another possibility is minus pi, right? It's the same exact point. If at t equals 0, the particle is here, when you start this stopwatch, the particle happened to be here, then phi of 0 is going to be, you can write it as 3 pi over 2, or you could write it as minus pi over 2. So you're measuring the angle negative going from the x-axis this way. So that means that your initial phase, as we're going to call it, your initial phase is, let's say, let's choose one, minus pi over 2. The other one also works. So if that's clear for circular motion, then things are going to be clear for oscillatory motion, hopefully. Because as we said, for every oscillatory motion, we can think of a circular motion that matches it perfectly, right? So you can think of a equation relating to a harmonic oscillator, about the phase, for example, the initial location, velocity, or whatever. You can think of the analog, the equivalent of that motion, which is circular motion. So let's see if that works. So this object, this oscillator with mass m, constant k, moves back and forth, and we said that we can describe at all times the location of this guy. It's going to be a function of time, and we say that the function that somebody found some time ago, a long time ago, was this, right? That should work for any oscillator. What's going to be different depending on the constants or the mass and the spring constants is this, and you can change that. And depending on the initial condition, you might have a different phi 0, depending on how you started this motion. So for example, if at t equals 0, the oscillator was here, and that coincides with the amplitude of the motion. So it started with velocity equals 0, you stretch this thing, and you let it go. At t equals 0, you let go of the block. How do I describe what does the position of this system, of this block, what does it look like, the function, position as a function of time? That means, how do I choose phi 0? What is the equation that is going to describe the motion of this guy after t equals 0? So it's going to have some amplitude, right? That a has to do with the maximum displacement from the equilibrium location. It's going to be a cosine function. It's going to have an omega t, but I have to decide on the phase. What kind of phase do I put here to make sure that at t equals 0, the oscillator is here? Should it be 0, pi over 2, pi? It should be 0. The phase, the initial phase, is going to be 0. If at t equals 0, the oscillator is there, that means that the initial phase that you're going to use to describe that motion is going to be 0. Right? Replace that here, and you see that x is equal to a at t equals 0. Which is what you have, correct? X is equal to a cosine of 0 plus 0. That's cosine of 0 is 1, so that gives you a. What is you could have answered that question immediately. I don't know if you answer immediately in your mind. But to answer immediately, look at the circular motion that corresponds to that. If at t equals 0, the oscillator was all the way to the right, the particle moving in circular motion that describes that corresponds to that oscillatory motion is located here, right? And the vector position of that particle makes an initial angle of 0. All right? So that tells you that the phase of the circular motion and the phase of the oscillator, the initial phase, should be 0 to describe that initial condition. What if at t equals 0, the oscillator started here? at the equilibrium point. How do I describe the motion of the oscillator after that time? Phi 0 equals what? Anybody? Anybody want to say what the answer is? Pi over 2. What about minus pi over 2? Should be the same thing. Pi over 2 or minus pi over 2. Well, how come? So let me write that down. Pi over 2 or minus pi over 2. How come for this I get a unique answer? I mean, I'm getting two answers, sorry. But for this, for the circulatory motion, the circular motion that corresponds to that, I never get two answers. The answer is always unique. Exactly right. So if I tell you that the block is at t equals 0, is at the equilibrium, I'm not giving you enough information. You need to know, was the block moving this way or was it moving that way? Because that's very different, right? So for this to be uniquely determined by the initial condition, I have to tell you which way was it moving. So if I say the block is at t equals 0, is at equilibrium, and it was moving to the left, then the answer is unique. And the answer is what? Pi over 2 or minus pi over 2? It should be pi over 2. Why pi over 2? What is the particle, the particle in circular motion that is tracking this block? What is that particle doing at t equals 0? It should be here, right? Because when the particle is here, it has a velocity going that way. It's tracking the motion of the block. If the particle was here, which will be the case for minus pi over 2, the motion of that particle would be to the right. Remember that the particle is always tracking the motion of the block. Okay? So this is what's consistent with this. So only pi over 2 works, not minus pi over 2. So once you know the initial position and the initial velocity of the particle, that means what is the particle doing at t equals 0, then the phase, the initial phase, is determined uniquely. All right? If at t equals 0, your block started there, what is your initial phase? Initial phase? Negative pi or pi, same thing, right? So your initial phase is going to be pi or negative pi. That is not ambiguous. It's not the same as pi over 2, which is up here, and minus pi over 2, which is down here. Those are two different angles. Pi or minus pi are the same angle, so we're not having any ambiguity there. Spending a lot of time on this because, like I said, this is very important for you to understand. Last one. If at t equals 0, the oscillator was here at the equilibrium point. Again, I have to tell you, was it moving to the left or was it moving to the right? Well, if it was moving to the right, then your phase, initial phase will be what? So your initial phase would be, where is the particle that is moving in circular motion that is tracking this block? Where is it? Should be either here or here, right? Because it's at the origin of the x-axis. We said that this one would give you a initial phase of pi over 2, and the particle, if it was here, will be moving to the left. That's not what the block is doing. So the particle must be here. If it's tracking this block, it must be down here with velocity to the right. That coincides with this. That is 3 pi over 2, or if you want the same angle, you can describe it as minus pi over 2. All right? Any other initial condition between these four, of course, is possible. The initial phase could be anything between 0 and pi or 0 and minus pi. So it's going to depend on where the particle is, your position, and your velocity. Those are the two numbers that you're going to need to specify phi 0 precisely. We'll do that later.